Okay, love dynamics. Let's study the mathematics of Selena Gomez and Justin Bieber's on-again, off-again relationship. Okay. So first let's define the function g of t as being Selena Gomez's love for Justin Bieber. And let's define the function b of t as being Justin Bieber's love for Selena Gomez. Okay. So when g or b are positive, then that means love. And conversely, when g or b are negative, that means the opposite of love. So, hate. Love-hate. So let's set up a system of differential equations that model their relationship. Okay, so I'm sure both of these people are perfectly fine people. I'm actually going to give Selena Gomez the benefit of the doubt. Okay, so let's say that Selena Gomez's love towards Justin Bieber is related to how much she loves Justin Bieber and how much Justin Bieber loves her. Okay, so when the relationship is going well, she's in love with him, he's in love with her, and her relationship just continues to grow and grow and grow. Okay, like a healthy, normal person. But now, let's say that Justin Bieber is not a well-rounded, normal, healthy person. Let's say that his love for Selena Gomez is modeled like this. Okay, so you can see his love for Selena Gomez depends on her love for him and his love for her. But you see there's this negative relationship here between Selena Gomez's love for him, which results in a situation like this. When Selena Gomez is in love with Justin Bieber, his love for her begins to decrease. Okay, so he doesn't like it when he feels like someone's getting close to him. But the opposite is also true. When she begins to not like him, he gets a kick out of that, and his love for her begins to increase. Okay, so let's rewrite this system in matrix form. Okay, so this system up here and this matrix representation are equivalent. Okay, when you multiply this matrix by this vector, you can see that you end up with this system that we started with. Okay, so how are we going to solve this? So we know that the solution to a system of linear differential equations is as follows. Lambda is an eigenvalue of the matrix A, and V is an eigenvector associated with lambda. Okay, so basically this system of differential equations is reduced to an eigenvalue problem where we're looking for eigenvalues and eigenvectors. So let's do that. So in order to find the eigenvalues, we need to solve this equation. Okay, so I'm not going to get into where this comes from, but it has to do with the nature of eigenvalues and eigenvectors. Okay, but the purpose of this video isn't to teach you how to solve the eigenvalue problem or how to solve a system of differential equations. Basically all I want to do is come up with a model of Justin Bieber and Selena Gomez's relationship, and then plot it, and then see if we can predict how it's going to go. Okay, so from here, when we plug in lambda into the matrix A, we end up with this. Okay, and this results in the eigenvalues. Okay. So here are our eigenvalues. So what's nice about complex eigenvalues is that you only need to find one eigenvector, because when you look at the real and imaginary parts of the eigenvector that's associated with this eigenvalue, you end up finding both linearly independent solutions. So let's do that. So let's look at this. Let's find the eigenvalue associated with this. So we end up solving this equation, where v is the eigenvector. So when you plug in lambda equals 1 into this equation, and you plug in the matrix A, you end up with this. And you can see clearly that when v1 is 1 and v2 is I, you have, so for the top part you have minus I plus I is 0, that's good. And you have minus 1 plus 1 is 0. Okay, so indeed v is 1I is our eigenvector associated with lambda 1. So we've basically solved this system already, but I'm going to simplify it a little bit. So our solution looks something like this. Okay, so there's a constant there. I'm going to sort of leave off the constants until the end. Okay, so, and I think I might have left off that. Yep, okay, so there's of course there's t's there. These are functions of t. Okay, so that's lambda 1 t, and of course there's our eigenvector. So as I said, I'm not gonna look for the other. I'm not gonna use lambda 2 equals I 1 minus I and look for the second eigenvector, because when I split this up into its real imaginary parts, I end up finding the two linearly independent solutions. So let's do that. So like I said, I'm going to leave off the constant terms here. So we end up having something like this. IT. Okay, and from Euler we know that. Okay, so it's going to help us simplify this. Okay, so included in this is I. I is just a number, so I can just include it in this coefficient here. Okay, so now let's look at the phase plane. So just to get an idea of how these solutions behave, we're going to let b equals 0, and then we're going to look at g squared plus b squared. Okay, so when b equals 0, what happens? We have a e to the t cos t squared, and what do we have for b? We have a e to the t minus sine t. So, okay, and we can rewrite this as a squared e to the 2t and cos squared t plus sine squared t. Okay, so what's this here? That's a circle. As t increases, you can see that this equation here is representing a circle with an increasing radius. Okay, so let's say that they meet each other and they're interested in each other. They're both attracted to each other. So let's say that their initial condition is right there. So G and B are both positive, so they're both feeling each other a little bit. But it's not very positive, so they have that initial attraction. So what does it mean to have a circle with an increasing radius like this? It means that from that initial condition, their relationship is going to behave something like that. So basically, it means that their relationship is going to spin out of control. Alright, so let's have a look at this phase plane in MATLAB. Okay, so I'm going to call the function ppLane8 in MATLAB. Input our system. And I'm going to plot the direction field. I'll change my axes here. Okay, so here's the direction field for this system. So like I said before, let's see what happens when they begin their relationship with these initial conditions. As you can see, their relationship spirals out of control. And actually, no matter where or how their relationship starts, every single time it spirals out of control. Okay, so maybe this can explain why they appear to be a typical on and off again type of couple. Okay, so thank you very much, and talk to you later.